Hi Chem 1. Today in 2.5 we're going to talk about why chemical reactions happen at all with energy and entropy. Energy is the ability to do work and produce heat. We know that energy is a big player in chemical reactions. We see endothermic and exothermic reactions, which we'll talk about here in a little bit. But the first rule you have to understand is just like we have a law of conservation of matter, we also have a law of conservation of energy. Energy can't be created or destroyed. It can be transformed into a different form, like mechanical or heat, or it can be transferred to a different object. But it has, with however much energy we started with before a chemical reaction, that's how much energy we have to end with. One thing to be mindful of here is the difference between the system and the surroundings. A lot of times we observe the surroundings of a chemical reaction, not the actual system. For instance, if you're burning a log of wood at a campfire, you don't observe the system. You feel the heat in the surroundings. So the process is exothermic, and therefore the heat that's given off you feel in the surroundings. All right? You're not actually touching the chemical reaction. The system plus the surroundings would be the universe, or the universal amount of energy that we have within that chemical reaction. The reason it's important to understand system and surroundings is because it changes our interpretation of the words endothermic and exothermic. You may know at this point that endothermic is when heat is required, or heat is absorbed, or heat is entered. I always think endothermic, heat enters. And then exothermic, I think heat exits, or when a chemical reaction releases energy. The thing with these two terms is it doesn't always have to be about chemical. We can use endo and exothermic in terms of physical changes like phase changes. So if we take a look here, if we look at the top, we have physical changes. And therefore, if heat enters, that phase change might go from a solid, liquid, to a gas. If heat enters into an ice cube, it's going to become a liquid if we go through the melting point. And then if heat exits, we go from a gas to a liquid to a solid. We would freeze, liquid water to a gas. The problem that a lot of times happens here is that when you think of endothermic or exothermic, a lot of times kids think about if it feels hot or cold. That's a mistake, all right? Because if I think of endothermic, heat entering in a physical change, we're going to go from solid frozen water to liquid water to gas. That feels like it's getting hotter, which it is because heat is entering. And in exothermic, we would say, oh, it's getting colder. So what will happen is you could say, okay, endothermic then is hot and exothermic is cold. But with a chemical reaction, that gets flipped around because you observe the surroundings. So for instance, a chemical reaction where heat enters, the heat is going to enter the reactions and the surroundings are going to get colder. And therefore, you're going to observe cold. And in a chemical reaction that's exothermic, heat is going to exit. You're going to observe the surroundings and you're going to feel heat. So what I'd really encourage you to do is not associate endo-exo with hot, cold. Think about the system and ask yourself, is heat going in or is heat leaving? And then identify it as endo-exo. One way energy can be measured is with energy calculations using something called a calorimeter. A calorimeter is something that physicists and chemists would use to burn a substance or heat up a substance in an enclosed space. And typically that heat that would be given off from that substance would then be transferred to water, and using the temperature change, we could figure out how much heat that object produced or how much heat that object can hold. The equation used for this is something called Q equals MCAT, or Q equals mass times the specific heat times the change in temperature. You could also do Q equals mass times the change in enthalpy, which we'll get to later. So one of the terms in that equation, probably the C term, is something you're not too familiar with, which is called specific heat. Specific heats are a specific physical property for a substance, and it tells us how much heat is necessary to get that object to change 1 degree Celsius or to change temperature. So this is something you probably understand. You can add a lot of heat to a pot of water, and the metal pot will change temperature very quickly, and the water inside will take a long time to change temperature. Why is this? It's because water has a very high specific heat. Water requires lots of joules of energy to change temperature. Where something like metals, they typically have a specific heat that's below 1, meaning they do not require a lot of energy to change temperature. So depending on the substance, that's going to change how much heat is required to change its temperature, which is why it's part of that Q equals MCAT equation. Notice even for water, it has different specific heats depending on what phase it's in. So let's do an example here. We have 10 grams of water and it's heated from 21.5 to 35.6. How much heat is required? So the second we are asked about heat, we would write down, all right, we got Q equals MCAT. Q is the amount of heat. That's the variable for heat. So Q we do not know. We have a mass of 10.0 grams. It doesn't say anything about C. And then we have our temperature change, which change in temperature is going to be TF, the final temperature, minus the initial temperature. So this would be 35.6, which is my final temperature, minus 21.5. And you might be thinking to yourself, well, then we don't have enough information. So technically we do. Water is the one specific heat that you need to know, and it is on your equation sheet. So if you look, water has a specific heat, C equals 4.184. And in this case, we're just going to use 4.18 because 10 has 3 sig figs. So I'm only going to use 3 sig figs within my constant. So now all we have to do is calculate our answer. So if we look here at the completed problem, we get 590 joules. Notice that our answer has 3 sig figs. That's because 10.0 had the fewest number of sig figs, which was 3. Also, I would make sure that you do your delta T subtraction before you get to the multiplying or typing it into your calculator, because you might have order of operations issues if you don't. Here's another one that's a little different. We got 145 grams, so that's our mass. Here's our temperature change. And then in this case, it gives us 5,750 joules. This is Q. So in this case, if we write out Q equals MCAT, we know Q, which is 5,750. We know our mass, which is 145. It asks us what is the specific heat. So it wants us to find C. And then we would do 45 minus 25, which is 20. So why would this kind of equation be important to know? Well, in this case, we would be able to identify the unknown substance by its specific heat. There are plenty of charts you can find online with lists of unknown substances and their specific heats. So if we could calculate the specific heat, we could theoretically figure out what the substance is. And if we would do that math correctly, we'd get an answer of 1.98 joules per gram degrees Celsius. All right, we've spent most of our time here talking about how energy influences chemical reactions, endothermically and exothermically, and how we can calculate that with Q equals MCAT. There is another natural phenomenon that kind of pushes chemical reactions forward, which is called entropy. Entropy is the idea of chaos or disorder. Things tend to move toward randomness. Things typically, chemical reactions typically don't organize, they tend to disorganize or become simpler. So to understand that term of entropy, let's look at some of these examples we have here, which some of them are chemical and some of them aren't. Organizing a silverware drawer. Did entropy increase or decrease? Just replace the word entropy with disorder. Did disorder increase or decrease? Well, if we were organizing, that means entropy or disorder decreased. Dissolving sugar into iced tea. So sugar is a crystal and water, okay, or the tea is a liquid, a solution, which we'll talk more about later. But when you put that sugar in there, it's going to decrystallize and dissolve. That means it's going to become more disordered. and therefore the entropy is going to increase. Melting an ice cube. This is going to test your knowledge of phase changes from before. If we're melting an ice cube, solids, remember, have molecules and particles that are very organized. And if we melt it into a liquid, we get more disorder, we get more fluidity, more randomness in the particle movement. And therefore, this would be an increase in disorder, an increase in entropy. Crystallizing iodine vapor. If you're crystallizing, if you're making a solid, things are becoming more organized. Crystals have a very organized pattern of how those molecules and particles sit together. So in this case, entropy or disorder would be decreasing. And that's honestly all we're going to cover about for entropy right now. We'll talk more about it later in the second semester. So here's the big point. Here's what drives chemical reactions. As we observe in nature, matter tends towards low energy and high entropy. So when we look at chemical reactions, typically the molecules that are on the product side will typically have lower energy states and have higher entropy states or be more disordered than when we began. So if you think about like burning a log of wood, that log of wood has very complex molecules like carbohydrates and proteins that were built within the tree structure. And when you burn it, you're breaking those molecules apart into lower energy molecules, and they're becoming more disorganized and dissipating typically into a gas. So just remember that's a really important key that we're going to hammer on the rest of the year. Things tend toward lower energy and higher entropy or more disorder. Good job today. We learned about energy, entropy, how those are involved in chemical reactions. Keep working hard. We'll see you soon.